Okay, let's get started with the lecture, which is about the design of LLC resonant converters. This is another very interesting topic in resonant converter series. If you remember, we talked about the basic resonant inverters, then we moved to the DC to DC, series resonant converter, parallel resonant converters, series parallel resonant converters, and also now we're moving to the design of something practical. Something is used extensively in the industry, which is the LLC resonant converter. This is used to be called an LLC resonant converter because we have two inductors. One is the resonant tank inductor and the other one is the transformer inductor, okay, or the coupled inductor value, which is the magnetizing inductance. We have L and C resonant tank, and also we have inductance from the transformer, the coupled inductor. Now again, our aim here is to make sure that we have the maximum power or the maximum gain from the combination of these components. Note here that we have a full bridge, because now we understand well the operation of the inverter. So we expect that the output here is a square wave, right? And this is V plus minus VDC, not plus minus VDC over 2, because we have a full bridge inverter, okay? And on the output here, we removed the inductor here because we don't have any capacitor. We have transformer here, okay? So we can add a capacitor on the output to make this output as a voltage source, no problems. Okay, let's look at the equivalent AC circuit of this converter. Here we replace the input with an AC square wave voltage source, and the output we replace it with the equivalent resistance. Here we have the LM, the magnetizing inductance, and we have CR and LR. Now let's define these values. The reactance XLR is equal to how much? Omega LR. And XCR is equal to how much? 1 over omega CR. And for the magnetizing inductance, XM is equal to how much? Omega LM. And again here, I will obtain the equivalent reactance here and the equivalent reactance here. Let's say this is ZY and this is ZX. So V out over Vn is equal to how much? ZY over ZY plus ZX, right? So that's what we will do now. So here we have VCD over VAB. The equivalent for the output term, ZY is equal to how much? JXMRE over JXM plus RE, and for the lower term, JXMRE over JXM plus RE plus JXLR minus JXCR. Everything is there, just we need to make some mathematics, some simplification. So here, VCD over VAB will bring the relationship first, the relation between the input and the output. Then after that, we'll go for the design procedure for this converter. So VCD over VAB is equal to how much? In this, if you try to simplify it, you'll find this is JXM times RE over JXM times RE plus JXLR minus JXCR times JXM plus RE. Now divide by the upper term, you'll find that VCD over VAB is equal to how much? 1 over 1 plus JXLR over RE minus JXCR over RE plus XLR over XM minus XCR over XM. Again, take the imaginary part together and the real part together. So VCD over VAB, it will be how much? It will be something like this. This will be 1 over 1 plus XLR minus XCR over XM. This is a real part, and this is J times XLR minus XCR over RE, and this is the imaginary part. Now we need to take the amplitude, the magnitude for the first harmonic, okay, for the first harmonic. And we know now the relation between the V out and VCD. No need to repeat this one. VAB and V input. So V out, first harmonic, over V input, the first harmonic, is equal to how much? So the input will be how much? Plus VDC minus VDC, not VDC over 2. So this square wave VDC, and this is how much? For VDC over pi. Okay, not VDC over 2 over pi, no. It will be VDC. So this will be how much? 8 over pi square. Okay, this came from the relation between V out over V in. Okay, and then this term will be same, 8 over pi square. This came from the relation between V out and V in. Okay, and then this will be the amplitude. It will be the root square of this term squared. So this will be 1 plus how much? Omega LR minus 1 over omega CR all together over omega LM, and this will be plus 1 omega LR minus 1 over omega CR over RE. Because this is XLR and XCR, we just substitute by their values with respect to the frequency. This will be squared. Now again, let's move for more simplification for this one. Just we can divide by their values. So here 8 over pi squared over 1 plus LR over LM minus LR over omega squared CR LR LM, all this will be squared, right? Plus omega LR over RE minus 1 over omega CR times RE, and this will be squared as well. Okay, so this is V out first harmonic over V in the first harmonic. Now we need to define the Q values to make this equation like more simplified. Define the Q values, omega naught and omega x, and put them in the form. Now let's define Q values. So Q here is how much? Omega naught LR over RE, and also it can be 1 over omega naught CR times RE, and similarly omega naught will be how much? 1 over the root square of LR CR, and omega x is how much? Omega over omega naught, or the switching frequency over omega naught. Take these values and put them in the previous equation. You will get the following: V out 1 over V input 1. This will be equal to how much? 8 over pi squared. This is 1 plus LR over LM times 1 minus 1 over omega x squared, and all this squared, plus Q squared times omega x minus 1 over omega x. So this is the relation between the output voltage and the input voltage. We can define the relation between the equivalent resistance and the load resistance, the resistive load on the output. Okay, but here we have a problem in this converter. We have a transformer, so we have to include the transformer ratio N1 over N2. Okay, so we can say that RE is equal to how much? 8 over pi squared times RL, but also times what? N1 over N2 squared, which is the transformer turns ratio, N1 over N2. Omega naught, as we said, is equal to how much? 1 over LRCR under the root square. Okay, and also we need to define the relation between the magnetizing inductance and the resonant inductance. Okay, we need to find the relation between this value and this value. This is very important. This is LR and this is LM. Okay, because for the series resonant converter, LR is fine, but here we have another component. This component will affect the behavior of the what? Of the curve, okay, of the output voltage. So we'll define like LM plus LR over LR. This it can be defined by a value of M, for example, okay, for simplicity. And then after that we'll change this value and see the effect of this relation. If, for example, if the M value is large, which means the magnetizing inductance is larger than the resonant inductance, okay, or much larger than the resonant inductance, how the curve, how the output voltage over the input voltage looks like. This is very important, the relation between the magnetizing inductance and the resonant inductance. If the value is very small, you will see that the curve behavior will be changing. It's different. So we need to keep this in mind. Okay, so here we have M, which is equal to how much? LM plus LR over LR. We have the equivalent resistance. From these definitions, we can redefine V out over Vn. From this also we can say that LM over LR here for this one is equal to how much? M minus 1, right? M minus 1, and we can redefine or rearrange this equation. V out over Vn first harmonic is equal to how much? 8 over pi squared times omega x squared over omega x squared plus LR over LM times omega x squared minus 1, and all this will be squared plus q squared omega x squared times omega x squared minus 1 squared. Redefine this equation again by using M value and omega x and other things. You'll find that we have again a function of a q factor, M value, and omega x. These three things, they will define the shape of the resonant behavior or the resonant curve. Okay, the V out, the gain, V out over Vn. This will be again V out first harmonic over Vn, and it will be 8 over pi squared times omega x squared times m minus 1 over the root square of m times omega x squared minus 1 squared plus q squared times omega x squared times omega x squared minus 1 all squared times m minus 1 squared. And this is the final equation, the relation between the input voltage and the output voltage for the LLC converter. Of course, you can use the previous one here, but here we have only LM over LR. You can say LM over LR something Z or something, is up to you. Okay, if you want to make a different definition, it's up to you. Now let's move to the design procedure. Now we have the equation. How we can use this equation to make our design, to give our values for the LR, for the LM, for the CR, right? For selecting the switching frequency, how we can use this. Okay, so number one, we need to select the Q value. Okay, the Q value. Now for small values of Q, okay, we have higher boost gain. Okay, so we can achieve higher boost gain, but the response to the frequency modulation in the above resonance region is low. Now we'll see how this can be translated on the figure. You'll find the frequency is like we have a small range of frequencies within a high range of gain. Okay, so this is sometimes makes problems, sometimes it's okay. So we'll see now this thing. So for small Q values, higher boost gain is achievable, but the response to the frequency modulation in the above resonance region is very low. Accordingly, wide frequency range is needed to move from the maximum to the minimum gain. But for high Q values, okay, the response to the frequency modulation is higher, but maximum gain should be attained. So this is number one. So number one, we need to select the Q value. Number two, we need to decide the relation between the magnetizing inductance and the LR, the resonant inductance. So we need to select the value for M. So here, for lower magnetizing circulating current and more flexibility can be achieved if we have select a certain value of M. For large M values, the magnetizing inductance is large, okay, of course, and the magnetizing circulating current is very small, and then we have higher efficiency. For small M values, like if the relation between the magnetizing inductance and the resonant inductance, the relation between them is very close to each other, if their value is very close to each other, which means M is very small. So for smaller values, okay, small values can achieve higher boost gain, and small M value can also accomplish more flexible regulation since a narrower range of frequency modulation. But small M at fixed Q and omega naught cause smaller magnetizing inductance, and then we have higher magnetizing ripple and high circulating current and conduction losses. So we need to decide, we need to make some balance between selecting the values of Q, the values of M, and so on and so forth. Once we obtain these two values, once we decided which value of Q factor, we decide the curve. Now we need to find the maximum value, okay, the maximum peak for this curve, and see at which frequency we should operate. Now, for example, after that, you'll find that you have a region of choices, okay, like let's say if Q is equal to a certain value, for example, and you have your gain is, you need to find V out over Vn within a range. It depends on your application. Let's say the input, for example, is 30 volt and the output is 400, for example. So you need to decide which value of gain you have and what range you have. Let's say this is from 0.5 to 1. So you need to make sure that your curve that you are operating is within the range, right? Let's say it's 0.5, this is 1, okay? So you cannot operate, you cannot select this curve. You cannot select the M value that bring this curve, right? Or the Q value that brings this curve. So we have to operate at a curve that has this option. Let's say you are operating at from 0.5 to 1.2, so you might select a curve like this. So you have the option to move from this point to this point. This is the operating range, for example, because you need to change the frequency and also you need to achieve the gain that you have. Now for our converter, here we need to calculate the resonant tanks component, and this information are usually specified depending on the application or the manufacturer requirements. Like for example, application needs a specific value or the manufacturer asks for a specific value, so we need to achieve these values. So for example, in our case, the output voltage is given by 400 volt, okay, and the input voltage is given by a range from 18 volt to 36 volt. So this is the range. The minimum is 18, the maximum is 36. And the nominal voltage is 33 volt. The output power is 250 watt, and the resonant frequency is 100 kilohertz. So this is the requirement, the manufacturer requirement or the application requirement. What we need to do, we need to specify the transformation ratio N1 over N2, the turns ratio, which is how much in this case. We have the input voltage is 33 volt, the nominal value is 33 volt, and the output is 400. So the transformation ratio or the turns ratio in this case 1 over 12. So by this we design our transformer to be 1 to 12. Also, we need to think about the maximum gain that we need. So the maximum gain in this, if you look at G maximum, is equal to how much? It can be changed from which value to which value. We have 33 volt. Like if the input voltage is 18, so this is the maximum gain that we need. So if the input voltage is 18 volt, the output of the resonant tank will be 33. Okay, so 33 over 18, you will get a maximum gain of how much? 1.833. So this is the maximum gain. The minimum gain, if the opposite happen, 33 over 36. So this is the minimum gain, which is 0.917. Keep in mind that this will make the other boost, like the transformer will boost the voltage. Okay, we'll step up the voltage from 33 to 400. So for the resonant tank, the minimum and the maximum gain should be how much? From 0.9 to 1.8. Now we need to take these values and go and plot our figure and see what is the value for the equivalent resistance, for the inductance, capacitance, and so on and so forth. I wrote this code, which is defining the gain, the equation that we just obtained here. On MATLAB, it's very simple. Just you need to define this very accurately, make sure that there is no error in this equation. Okay, then we plot the figures, and I define the Q values from 0.2, 0.3, 0.5, 0.7, 1, and 6 to see a wide range of Q values, and also the values of M. Since we have these curves, then we plot them and see what is the maximum, what is the minimum gain, and pick one of the curves and decide what is the value of the Q, what is the value of M, and accordingly we can find the value of LR, CR, LM, and so on and so forth. So here I plot the figures. This figure when M value is 3, okay, and this when M value is 6, and here when M value is 15, okay. Now look, what we need gain from 0.9 to 1.8, right? So from 0.9, from here to 1.8, to this point, and here same, 0.9 to 1.8 here. So you need to decide which value of M you need and which value of Q according to what we have. If you look at here, for example, 0.9 is here and 1.8 is here. So high value of M is not preferable now, because you can see that we have only one option here and we will not be able to reach to the maximum, right? So this is not preferred. A smaller value also is not preferred, because yes, you can reach the value, but here for example you cannot reach, we need the peak, right? We need the peak value. This cannot be achieved here, and also you'll find that the curve here falling very fast. When you change a very small value of frequency, you'll find that the gain is changing very fast, which is also not preferable. We'll go for a larger value for M, which is here, I think 6 or 6 point something. It will be a good option for M value. So this is 0.9 and 1.8. It can be something like this here or something. So we can operate at this range of frequencies. For example, you need to decide the Q value as well. We need to decide which value of Q. Q is equal to 0.4, at Q is equal to 0.4, and at M value of 6.3. Why? Because this will bring us a maximum value here. We can reach a maximum value, a peak value, and also, so operating at resonant frequency, and also we can operate at a wide range of frequencies to change the value of the gain that we have. Once we pick Q and M, no problem. We can design, we can bring the values of LR, CR, and LM. Why? Because as again we said, omega naught is 1 over LR CR. We can get the values of this of the LR and CR. Q also is directly related to the LR and CR, and M value is LM plus LR over LR, right? So we have like 2 equations or 3 equations with 3 variables. We solve them, we bring the value of LR, LM, LR, and CR. Once we pick the values, which are the M, we said M is 6.3, Q is 0.4, and omega X minimum, the minimum value for the omega X is how much? Is 0.489. Once you pick these values, you'll find that you can easily obtain the LR, which is 2.25 microhenry, and CR, which is 1.13 microfarads, and LM, which is 11.93 microhenry. So you see here the relation between this and this is not very high, but also they're not close to each other. So here I put this one on MATLAB. We just need to specify the frequency. Make sure that you are operating at like the right frequency. Of course, for the resonant converters, you will find that because the relation between the resonant frequency and the components, there are standard values for the components, for the capacitors, inductors, and the resonant frequency is not always fixed. Like they're not always standard, right? If you pick a standard value for the capacitor and the inductor, you'll find that the frequency, the resonant frequency, is not a standard value. It's not 100 kilohertz or something. So it will find it difficult to exactly operate at the resonant frequency. If the discrete value that if your processor is like giving a very accurate discrete values, yes, you can operate at any frequency that you want, no problem. But this is not most of the cases, not most of the time. If you look at the output waveform, this is the value for the diode, the current within the diode 1 and diode 3. You'll find the current is taken one portion from this. This portion is taken from here, and this portion is taken from here. Exactly. And then here we have, when we switch between the diodes and the switches, you'll find that we're operating at zero current, zero voltage switching, so no problems. The conduction losses, switching losses will be minimum. Okay, why? Because we operate at resonant frequency, and life is easy. Okay, you can pick different frequencies. For example, if you want to design different application, like different input voltage, different output voltage. So that is everything for today. I hope that you enjoyed this lecture, and I will see you next lecture.